Okay, so enthalpy of reaction. We're going to derive the enthalpy of reaction, and then I'm going to show you how you can use this for conversions, aka stoichiometry conversions. Alright, so in the previous video, I showed you that the combustion of CH4 in a calorimeter, depending on the amount of CH4 that you start with, generates different amounts of energy, different amounts of heat. Specifically, I told you that for the first example, we generated negative 151.6 kilojoules based on having 0.1719 moles of CH4 initially. All right, now, if we actually take the ratio of the heat evolved by the reaction by the moles of CH4 that we have heat divided by moles, yielding a value of negative 81.9 kilojoules per mole. Okay, and the idea right here is that by taking the ratio, what I'm kind of doing is coming up with a single value that will represent the reaction of CH4. And if we look carefully and we do the same examination for the second example where I change the mass of CH4 to half a gram, which is the same thing as 0.03117 moles of CH4, in that case, we generated negative 27.49 kilojoules of energy. Taking the ratio of that heat with that amount of moles of CH4 yields, unsurprisingly, with the same value of heat per mole, kilojoules per mole in this case. Now, technically speaking, this is what we call the enthalpy of the reaction. We are finding out the heat using the ideas of the zero law of thermodynamics and the calorimeter setup, and based on the initial amount of the reactant, which is something you have to measure experimentally. If you don't measure that, then you don't know. You're none the wiser. But knowing the initial amount of the reactant and finding out with the experiment the amount of heat being generated allows you to find out the ratio, which is known as the enthalpy of the reaction. Okay, so delta H is the enthalpy reaction, and in the next lecture, I'm actually going to expand upon what it represents and what it fully tells you, and what are the things that we can find out with enthalpy. For now, I'm just kind of introducing it and kind of giving you a rudimentary relationship to regular heat, but now in terms of a ratio. Now, another thing that I want to discuss in the next lecture to some extent is the fact that much like heat associated with specific heat capacity, you can find the enthalpy by multiplying the change in temperature of a substance by something we call the heat capacity at constant pressure. And notice the different symbols right here, Cp. That's the heat capacity at constant pressure. And this particular heat capacity has different units. The units of this is not joules, grams, degrees Celsius. It's actually joules per mole Kelvin. And multiplying by the change in temperature in Kelvin gets you rid of Kelvin and leaves you with joules per mole, which you can then convert to kilojoules per mole if you need to. But this is a heat capacity that we can use to get directly to delta H. But another feature that I want to point out to you, which is going to be of use in an upcoming video, is the fact that delta H equals Q over N. So N times delta H has to equal Q. So that would be a nice way of kind of going back and forth between delta H and Q, simply by dividing or multiplying by the number of moles. All right, so we're going to use that feature in future videos and in the next lecture as well. But the one thing I want to emphasize now is that because enthalpy is a ratio of heat over moles, enthalpy can be used as a conversion factor. I'm going to show you an example that I kind of avoided in the past, but now I'm bringing it back and kind of giving it the full extent of the explanation now that we've talked about enthalpy. Here we have a reaction involving H2CO with sodium perchlorate yielding carbon dioxide, water, and then your salt. Now what I'm saying here is that the enthalpy of this entire reaction based on the moles of H2CO is negative 156 kilojoules per mole. So what I want to find out is how much heat is being produced by this reaction, like how much actual heat, not enthalpy, but actual heat. And so for that, we have to take into account that enthalpy is actually a ratio of heat over moles, so we can use it as a conversion factor. And what we want to do is start with the amount of the molecule, the reactant, H2CO. And of course, if you had the amounts for both reactants, you will have to first find out what's the limiting reactant, and based on the limiting reactant, you will have to find out the heat itself. But right here, this is just a regular stoichiometry problem. So starting with the 10 mLs of H2CO, we can use that along with the density to switch over to mass. Specifically, we have mLs on top, so we're going to place mLs on the bottom. The 0.815 grams go on top, so the mLs cancel out. Now the grams of H2CO can be changed to moles using the molar mass of H2CO, which happens to be 30.03 grams. So the grams cancel out, and now you end up with moles of H2CO. Now here is the kicker. This you've seen before. You've done this type of conversions going from volume to mass, from mass to moles. But here's what it's semi-new. Having the moles of H2CO, which is the moles that we're basing the delta H right here on, we can use delta H as a conversion factor. The negative 156 goes with the kilojoules. The mole has just a one placeholder as a number, but we have moles of H2CO on top, so we make sure to place 1 mole of H2CO on the bottom, and the negative 156 kilojoules go on the opposite end of the fraction. So moles cancel out, and all you end up with is the kilojoules, negative kilojoules. So you carry on the calculation, multiply 10 by 0.815, divided by 30.03, multiply by negative 156, then you find out that the final answer is negative 42.3 kilojoules of energy. This is how much energy in kilojoules you will produce when all 10 mLs of H2CO react away. Alright, and the big idea right here is that enthalpy, being a fraction, can be used as a conversion factor. But the other thing to emphasize too is that enthalpy is going to be a constant number no matter how much reactant you start with, because the enthalpy is not a single value, it's actually a ratio of values. Much like density has a constant value for a substance, provided the temperature doesn't change, the enthalpy will have also a constant value for a reaction, so long as the temperatures don't change too drastically. Alright, now in the next video, we'll talk about how heat and physical transitions come together in explaining the overall process of undergoing melting, evaporation, and so on and so forth. Okay, so we'll see that on the next video.